Welcome, everybody. Good evening, and welcome to the public lecture by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology at Stanford. My name is Nandu. I am the Outreach and Engagement Manager at KIPAC, and I will also be your main host today. Today, the lecture is actually going to be the last talk in our mini lecture series about dark matter detection. So you're all here just in time as we're wrapping up this lecture series. The previous two talks, we have introduced two different kinds of dark matter candidates, including some direct detection methods for wave-like and also particle-like dark matter. So today's lecture, I'm personally very excited about, is actually going to be discussing some of the possible dark matter searches with astrophysical objects, especially around the nearby star and planet systems. So before we start, I would like to get to have a big shout out to the entire team who is supporting our event today behind the scene. So for those of you who are in person, you might have already met some of the front desk staff and volunteers when checking in. Also, a huge thank you to our tech team right here, who's managing the live streaming. And also our KIPAC outreach team members, Na-Young Son and also Lori White, who will be joining us later. And specifically, I would like to introduce some of the online chat moderators who are all subject experts who are answering questions on the YouTube page. So I will let them to quickly introduce themselves. So first we have Javier.
Hi, everyone. I'm Javier. I'm a postdoc at the SLAC National Accelerator Laboratory here in Menlo Park, and I'll be happy to take any questions you have in the chat today.
Great. Thank you, Javier. Next, we have Richie.
Hello, everyone. I'm Richie. I'm a rising fifth-year grad student here at KIPAC. I mainly work on modeling galaxy formation, specifically dwarf galaxies. I run a lot of dark matter simulations. So I work more on the phenomenological side of things.
That's fantastic. And last but not least, we have Everett.
Hi, everyone. I'm Everett MacArthur. I'm a postbac at here at KIPAC, and I previously have worked on planetary formation stuff, and now currently work on machine learning.
Awesome. So as you can see, well, here in person, you don't get to interact with our chat moderators much, but if you're online, we welcome all kinds of questions and discussions in the live chat that you can see on the right-hand side. We welcome all kinds of questions and simply just ask you to be respectful to others. And for all the in-person audience that we have here, you all will get to ask questions during the Q&A, which is at the very end. And of course, after the event concludes, you'll also get a lot of time interacting with our speaker today. So without further ado, let me introduce today's speaker, Dr. Rebecca Leane, who is an expert in theoretical particle astrophysics. Rebecca is a staff scientist in the particle theory group at SLAC and also a member of KIPAC. She got her PhD from University of Melbourne and also did her postdoctoral work at the MIT Center for Theoretical Physics before joining SLAC. So Rebecca's research actually focuses on revealing the most fundamental nature of dark matter. And very recently, she's interested in exploring the astrophysical systems that can actually help us look for different dark matter candidates and also maybe other beyond the standard model physics. Yeah, so without further ado, Rebecca, I will turn this to you.
Great. Thanks very much for the introduction. Good evening, everyone. Welcome to Stanford. It's really a pleasure to be here today to share with you some of my own excitement about trying to understand this very mysterious matter that we call dark matter. So to start, this is a deep field image. So when I say a deep field, we're using a telescope to look very far away, very far back in time. So if you're a big astronomy fan, you might have seen an image like this a long time ago, which came from the Hubble Space Telescope. So it was called the Hubble Deep Field. We actually have a new version of this now from a new telescope that's an absolute powerhouse called JWST. So we just got this image last year. And what you're seeing in this image are stars and galaxies. So the stars that are the closest to us are mostly what you can see that have the lines through them. The lines are just telescope artifacts, but almost everything else you can see in the image are galaxies. So for context, we're all sitting here on planet Earth. We're going around the sun, and there are lots of other planets also going around the sun, and that's the solar system. But we're part of a much bigger sort of system called the galaxy. And in the galaxy, we actually have billions of stars and billions of planets. And for us, this is just the Milky Way galaxy. But out in the universe, there are so many galaxies. And that's what you can see in the image here. So in this image, where you see galaxies, that each galaxy itself has billions of stars, billions of planets, maybe one like us, maybe some life. And the really crazy thing about this image is if you were to take a grain of sand or something very small and hold it up to the sky, the amount of the sky that that grain of sand would cover would roughly be the amount of this image that we're actually looking at on the sky. So out in the universe, we have so many galaxies, we have so many stars. Really, this is very awe-inspiring. The universe is so vast. But when we look at an image like this, how much of the universe are we actually seeing? So we know from high school, where I see a few younger members of the audience will learn in high school coming up soon. Generally, we learn that everything is made up of atoms. So myself, everybody in the audience, you think about being made up of things like hydrogen, helium, oxygen, carbon, all the sorts of things that you see in the periodic table of elements. This is kind of the reference you might be used to thinking about what matter is. So everything is made of atoms. Is that true? Actually, everything, most of what you saw in that image before is only about 5% of the energy matter content of the universe. Actually, we don't know what about 95% of the universe actually is. So everything that you can see, everything that you're made up of, is not the same stuff as the rest of the universe, which is pretty crazy. So it turns out the bulk of the universe is dark stuff. So we call it dark matter and dark energy. So in my talk today, I'll be focusing on the dark matter component of the universe. Dark energy is something totally different, has different dynamics. It's a different type of problem we're trying to solve. So when I tell you that most of the universe is dark matter, I really empathize with you if you think it sounds crazy and made up. So I remember the first time I heard about dark matter as a teenager, and my reaction was, that's not real. I think scientists just don't know what they're talking about. Probably there's just some fudge factor. It's going to be like the ether. It's going to go away and it will be, just one of those embarrassing moments we had maybe in science. That was then until I started to learn a bit more about it. So now I'm clearly a dark matter expert, so I'm pretty convinced it exists. But the amount of evidence we have for dark matter actually is really overwhelming. This isn't just like something we don't understand that we just tried to sweep under the rug as some sort of fudge factor. We actually have evidence for dark matter across so many different length scales. So we see evidence for dark matter and we look back into the early universe. We see it and we look in galaxies. We see it and we look at so many different systems. So while I would love to tell you all about the different types of evidence we have for dark matter, that would take more than I possibly could fit into this lecture. So I'm just going to give you one example that I kind of like, and then tell you kind of briefly about some of the other ones, but I just can't go into detail on all of them. So the one I want to explain to you as an example of the evidence we have for dark matter existing is something called the bullet cluster. So at the beginning of the talk, I showed you this deep field image where you saw lots of different galaxies. So these galaxies generally are kind of whizzing around, and very often galaxies can just collide. In fact, one of the galaxies that's very close to us, Andromeda, is going to probably collide into us sometime in the future, but don't have to worry, it's not anytime soon. Galaxies in general, though, they can collide, and clusters of them where you have lots of galaxies can all really smash together as well. And this was observed in this system called the bullet cluster, so clusters of galaxies. So if you draw your attention to the top panel, if you ignore just the green lines for a second and have a look what look like kind of stars in the background, that's just the image we have from the Hubble Space Telescope, just seeing some stars in the background. Now, the green lines on top of that image what are called gravitational sort of contours. So you can think about these contours as being like when you see a weather forecast and you see, there's a really hot sort of cell that's moving around. The hottest is always in the middle, and it's a little bit cooler as you think about the contours as it, all moves across the land. So in these contours, if you're in the central sort of region, so either in the middle here on the left, in the middle on the right, gravity is the strongest. And if you're sitting in any of these other lines, gravity is just getting weaker. So as these systems are colliding, we have some very gravitationally dense regions on the side. So if we have a high amount of gravity, what that means is there's a lot of matter there. So we can think about the fact, just how gravity works. We're sitting on the Earth, we feel some force as we're pulled towards the mass of the Earth. If you just took the Earth out, we wouldn't have any gravitational sort of force anymore. So if you have gravity, you have to have mass. So what's happening in this image is that all these clusters are colliding. We see the bulk of the mass has to be out on the left and the right sides of the image. And what's interesting is we look at this bottom panel here, you can see the really bright region in the middle. So what's actually happening is as these galaxies are coming together and colliding, if you have the regular sort of matter, so everything from our periodic table of elements, everything we're made up of, the particles will hit each other and there'll be heat, there'll be friction, and you can just have a lot of energy and light sort of coming out. So this here is actually an X-ray, which is just like very high energy light. And we detect that with the Chandra telescope. So what this actually means is that as all of these galaxies have started to collide, there's been a lot of friction. The visible matter is kind of all hitting into itself. We're seeing all of these X-rays come out. But what's really weird is then it seems like the bulk of the matter is on either side of where the visible matter is. So there seems to be some other matter there that is not the regular matter that we're made up of. So just to make this a little bit clearer, I'm going to show you a cartoon. So this will be like a step-through animation to show what the picture is and why we think dark matter is what's causing this extra gravitational pull either side of the regular matter. So in pink here, regular matter, blue is the dark matter. So dark matter is also in the center of these blobs. There's just more of it, so it's kind of more extended. So we see these things are still colliding. The regular matter is really lighting up, makes sense, lots of friction. But the blue stuff, which is the dark matter, has mostly just passed through. And this would explain the image of how we see the bulk of the gravity coming either side of this collision. And you can't really explain this event if you don't have some new matter that doesn't interact very much. So it has to be some other new type of mass or particle that's just passing through, doesn't mind about the collision, it's not really colliding, it just passes through and sits either side. So this is one piece of evidence for some extra mass being there that isn't the regular sort of stuff that we're made up of. Now, overall, what do we actually know by now about dark matter? So that's one piece of evidence. I told you there are many different pieces of evidence. But overall, when we try and piece all of the evidences together to get a picture of what we do understand, there are some things that we do have a consensus about in the community. So first of all, we think it's about 5 times more abundant than the regular matter. And we think it doesn't interact with light. Or at least if it doesn't interact very much with light. Now, these 2 pieces of evidence come from, these pieces of information about dark matter come from something called the cosmic microwave background. So that's the image that you see on the right here. So this is just like relic radiation from the early universe. And the reason that we learn about these facts from dark matter really is just by looking at the patchiness of this image, we can kind of decode what physics is happening to get this patchiness, very roughly speaking. We think that dark matter also provides the large scale structure of the universe, and therefore it's non-relativistic. So to explain this point, this image on the right is for a simulation of what we think the universe can look like on really large scales. So going back to the image I showed you at the beginning of the deep field where we see lots of galaxies, you could imagine really having lots of galaxies all throughout these filaments. So it's just really like a large scale structure, a backbone to the universe, if you will. And in each of these filaments, you have like gas and dust, and this is where you would expect all the galaxies to form. And now if you had dark matter that was moving around too fast, which would make it, say, relativistic, for example, you just wash out a lot of the structure. And then you just wouldn't have galaxies appearing in the way that they do today. Another point is that we think dark matter forms halos around galaxies. So the reason we think this is that we've looked at many, many types of galaxies, and we can look at the speed that all the stars, the planets, the gas, everything is rotating around the center of the galaxy. And what we expect just from regular sort of physics calculations is that as you move further out of the galaxy, so if you start towards the center, you go further out, eventually the speed should just decrease. So once there's no more matter there, you shouldn't be going around too quickly. But instead, what we see time and time again in so many different galaxies is really just that instead, this sort of flat shape is observed, which implies you need to have more matter on the outside of galaxies to have them spin around as fast as they do. We also think that dark matter is stable on really the scale of the age of the universe. And this is just because, well, if dark matter exists, it has to explain all of these phenomena that we observe everywhere in the universe. It has to still be here. So when I say stable, I mean it just didn't decay or disappear in any sort of way. It has to still be around. So all of these features just cannot be explained by anything in the periodic table, anything that we're made of, any particle that we know. So we need some new particle if we want to explain what we observe everywhere throughout the universe and understand what the bulk of the matter of the universe actually is. So those are some of the things that we know about dark matter, but in reality, the number of things we don't know about it really is much, much larger. So we don't know what dark matter is made of. We don't know if it's one particle. We don't know if it's a whole bunch of particles. We don't know within that sector if there's lots of particles, they all interact with each other. Maybe they have secret interactions that we just haven't observed. We don't know where dark matter came from, which is, if we have dark matter particles around in the universe today, usually you want to have some mechanism to explain how they got there. So we had the Big Bang. How did they exactly get made? We don't know. We also don't know if it interacts with the regular matter. So does it even interact with us and our detectors? We'd really like it to interact with us so we can actually detect it and understand it, but there's no guarantees. It doesn't have to interact with us. So while we have lots of evidence for dark matter's existence, all the evidence we have to date only comes from its gravitational interactions. We've never observed it anywhere in any detector. We haven't seen it light up in anything we've ever done in the lab. So you can imagine if you sit with this picture and you think, I would love to discover dark matter. What do you do? How do you find something when you have almost no idea what it is? And this is a question I'm faced with in my research. This is what particle theorists are faced with all the time when we try and think we want to discover dark matter. How do we do it? There are so many different possibilities for what it could be. Maybe you have some mathematical theory. Why should it be the right one? Why should your idea for your search strategy be the right direction to go? So my approach to trying to answer these questions really is focusing really broadly on new types of search strategies. So far, dark matter hasn't shown up except for through astrophysics and cosmology, through gravitational interactions. So to me, thinking about new searches in the areas we've already seen dark matter, perhaps is the way to go. So the fact that dark matter has only kind of revealed itself through astrophysics and cosmology, to me, makes it its natural habitat to go looking for it. I also love to think about astrophysical systems, to be honest, just because they're really fun. So there's such a wide range of diverse systems that exist out in space. We have so many things that are just exploding, colliding, doing all sorts of really crazy things. The universe has been running experiments for us over the whole age of the universe. So we think about the bullet cluster was just smashing together galaxies, and we saw, okay, looks like actually some dark matter is there. So what I find really fun in my research is thinking about how can I be creative and thinking about the observables we already might have just sitting there. All these things are happening out in space. How can we exploit all of these systems to try and reveal some potential dark matter hint and try and go forward from there? I also like to think about using the latest astrophysical data sets. And the reason for this is if you have some new search idea, you also want to be the one to find it. At least that's what I want to be. I want to be the one that actually finds it in the data. And the reason why I think astrophysics is a great place to be doing this is just the wealth of new telescopes and technologies that we're going to have in the next decade. So I told you at the beginning, this JWST telescope, absolutely amazing. But that's not the only one. We have some that I'll tell you about shortly that hopefully will launch actually in the next few years. And so I think there are lots of really exciting opportunities to try and find dark matter using this wide range of multi-wavelength telescopes. All right, so now to get into some of the searches. Just to be really clear, I'm going to show you now here just an image of a galaxy in a dark matter cloud. So this is what I'm thinking about when I say there's a dark matter halo that's around the galaxy. So in case when I said halo, you were thinking about maybe like an angel's halo. It's not like a donut shape. The halo we mean when we talk about a dark matter halo really is like a sphere. So it's a sphere with most of the dark matter in the center that kind of gets a little bit less of it as you go further out. So there's about 5 times more of it than the regular matter. So that's why you see really just this huge amount of dark matter and then a galaxy. So this should be true in our galaxy. It should be true in the bulk of galaxies that you look at. So if we have this big dark matter halo that we're just sitting in, how could we maybe detect the dark matter particles that are there? So one idea that I've been very interested in recently is thinking about how you can capture dark matter particles using stars and planets in our galaxy. So the general idea is that you have throughout the galaxy lots of stars and planets just peppered everywhere. And in that halo, the dark matter particles are just whizzing around. So what can happen is one of the dark matter particles can just come smash into the surface of a star or a planet, like what you see in this cartoon up here. And if it hits into the surface of the star or the planet, just like if you took like a ball and threw it at the ground, it bounces off and loses some energy. So dark matter can scatter, lose some energy. Maybe it scatters again and it loses even more energy. And if it has enough these scatters, it might lose so much energy that it can become gravitationally captured, which is, so it whizzes in with some velocity, some speed. And then just after scattering, the gravitational pull of the star or the planet can pull it in and then capture it. So now dark matter is going to stay inside a star or a planet. But remember, we have this huge halo of dark matter particles. So there's lots of them there. So over time, what actually would keep happening, so dark matter particles keep smashing into the surface of these objects, keep bouncing off, losing energy, falling into the center and just becoming gravitationally captured. And after a while, you would just have lots of dark matter particles, a big population of them just sitting in the center. And what actually can happen at that stage is they can annihilate with each other. So we don't know if dark matter would do this, but this is what the regular matter does. So when I say smash together and they can annihilate, you can think about matter and antimatter, like what we have in our regular sort of visible matter. So if you have matter and antimatter, you put them together, you're going to get a bit of an explosion. So they're going to annihilate. And just from conservation of energy, if you annihilate 2 particles, the energy has to go somewhere. So usually what happens is just a particle physics type of process, they transform into different types of particles. So you can smash dark matter particles together, particle, antiparticle. They can make the regular matter, for example. And if this process just keeps happening over time, you're dumping a lot of energy into a star or a planet. Because all the particles, dark matter particles whizzing around in the halo, bang, loses energy, goes inside, bang, explodes. That's lots of energy being released over and over again. And what actually should happen is the temperatures in stars and planets should be increasing. If dark matter does scatter with them and it does lose enough energy and it does annihilate, go bang, increase the temperature. We've measured stars and planets. We're going to do it even more in the future. This seems to be a good signature to look for. Are stars and planets the temperature we expect? So before I go into the details of some of these searches or particular types of stars and planets that we use, I just want to mention when you try and choose a particular target, there are some things that will make them optimal or not optimal. So remember I said that we have almost no idea what dark matter is. So we don't know what mass it has, so like how heavy it is. We don't know how much it interacts with us, if at all. So usually if we're trying to then really just broaden our discovery possibilities, we want to try and consider, as wide of a mass range as possible and as wide of an interaction range as possible as well. So depending on what properties dark matter has, it actually turns out that different stars or planets might be the best one to try and discover it. So to give you an example of what I mean about the properties that would make it important to find dark matter, one is just the radius of the object. So you can imagine if you just had a bigger star or planet, if it's bigger, the surface area is larger. So if dark matter is whizzing around, the chance of it actually hitting the surface is much higher if it's bigger. So probably it would end up capturing more dark matter particles and having more energy because the dark matter particles keep going in, bang, heating everything up. Another feature that we like is a high density of a star or a planet. So again, we don't know what dark matter is. If it doesn't interact very much, so if it's very weakly interacting, and you have a very dense star, for example, what happens is the dark matter particle go in, it just gets trapped very easily because it's so dense, with lots of things in there to scatter with. And usually if it's also dense, the escape velocity is pretty high. So it's hard for dark matter to get back out. The other feature we like is for the star or the planet to not be too hot. So first of all, if it's too hot, it's going to be hard to see any heating signal coming from dark matter. But also if it's too hot, actually you can just kick out the dark matter particles too easily. So you can think about all of the particles in the star, for example, they're kind of buzzing around if they have some temperature, and that temperature can just kind of go poof and push the dark matter particle back out, which will happen sometimes if it's too hot. So we want to optimize over these properties to try and find dark matter. The other thing we want to think about is what location do we want to use a star or a planet? There are actually lots of different places we have stars and planets in our galaxy. And you might wonder, why would I ever want to look very far away? You know, why would I want to look on the other side of the galaxy if I could use something very close by that maybe I understand better? The reason you might want to look further away, at least into the center of the galaxy, is that we think the most of the dark matter is in the center. So we think this just based on our simulations. There should be a lot of dark matter in the center of the galaxy, and it should be, you know, maybe 1,000 times more than what we have at our position on Earth. So if we're going towards the center, we can have maybe 1,000 times more. We don't know this number very precisely. It's just larger than what the local position is. And maybe we also want to think about some other clusters, like stellar clusters, where there's groups of old stars. Sometimes they can have a lot of dark matter also in that system. And if there's lots of dark matter there, there'll be more heating because you've just got more dark matter particles available to fall into the stars or the planets. And for the local position, I mean, we have less dark matter, but there's obviously the benefit that it's just close by. If you have something very close by, usually it's very easy to just see it, measure its temperature, or measure how bright it is, for example. So in terms of the location, the sorts of features that we want high dark matter density if possible. We also want close proximity if possible. And then we want low dust just so that we can actually see the star or the planet. If we have too much dust in the way, we won't see anything. And old environments are also good because usually they've just had some time to cool off. The younger systems usually are a bit hotter. All right, so just to recap what I've said so far, there are lots of different celestial objects. So celestial objects, I mean stars and planets. They're going to have different temperatures, different sizes, different densities, and all these different properties, as I'll show you soon, will make them optimal to find dark matter depending on what properties dark matter has, because we don't know what properties it has. There are lots of different search locations that we can use for dark matter in stars and planets. Generally, the sort of features we want are large dark matter densities, just because there's lots there to try and power the signal, something close by, something fairly old. All right, so there's a variety of dark matter signatures in stars and planets. I'm going to now focus on the dark matter heating that I've mentioned to you for many objects and locations. All right, so dark matter heating. All right, if we want to actually detect this, what do we have available to us? What telescopes do we have? We can't just come up with some idea and have no way to detect it. Otherwise, it's probably not so interesting. So the coldest planets that we have are about roughly minus 280 degrees Fahrenheit. So that's very cold. That's roughly what if we're on the surface of Jupiter, dealing with. So that's about the coldest that's there. So if dark matter is going to heat up any star or planet, it's obviously not going to make it go colder than what it is. So the minimum temperature will be minus 280 or so. And what that corresponds to on the electromagnetic spectrum, so when I talk about the electromagnetic spectrum, it's really just kind of like, well, visible light, we all know, that's what we can see. but there's actually a whole other range of wavelengths that exist that we don't unfortunately see as humans, but fortunately for us, we have technologies that can see them. So on the higher end, we have gamma rays, X-rays, UV rays, and the lower end, radio waves, microwave, and the infrared. So it turns out this temperature of about -280 is pretty far into the infrared. So that's the type of wavelength we're dealing with. So it's the bottom here. So for dark matter heating, all we're going to have is you have to go higher in temperature. If it heats up, generally we stay in the infrared, and in some cases, dark matter will push into the visible as well. So we need an infrared telescope or something that can see maybe the bottom end of the optical. And we have some amazing instruments that we can use to see this. So first of all, the Hubble Space Telescope, maybe you're most familiar with that one. That launched a good time ago. It's still taking data. So it can do the near infrared optical and actually a little bit into the UV. We have GWST. This is the new powerhouse on the block, launched Christmas Day 2021. It can see the infrared and a little bit into the optical. There's the Rubin telescope, the Rubin Observatory. We're awaiting data here. First light hopefully will be actually already next year. And in fact, actually many of members of KIPAC at SLAC have played a very important role in getting Rubin off the ground. So that can see near infrared and optical. We also will have the Roman telescopes. So there's just a bunch of telescopes. It's great. This one will also see the near infrared and optical, and we don't have the data yet. Hopefully it will launch 2027. So we have 2 great telescopes already active, and we have 2 more that might be able to see these signatures coming up soon. All right, so now I think hopefully I gave you enough background about how these searches work, why we're going to pick particular targets. Now we get into the fun part of actually talking about the targets and seeing what the implications are for dark matter. So first one is Earth. So we're all sitting on the Earth. So this seems like the most obvious thing to actually to use to start with. And for the Earth, actually, I told you about these telescopes, but on the Earth, you don't even need a telescope. We're just sitting on the Earth. We can try and take the temperature of the Earth. And before anyone asks, I'm not going to try and sell to you global warming is due to dark matter. So don't ask me questions about that. Okay. So for the Earth, we actually have already dug something like 20,000 boreholes across the surface, and these go a few miles deep. So geologists already are trying to understand the Earth. So we already actually have a lot of data. We know what the internal temperature of the Earth is. So this is kind of a slam dunk for us. We can already just compare the theoretical calculation for how dark matter would potentially heat up the Earth and see, is there anything anomalous there? Does it match what we see with the Earth? Or maybe we can exclude dark matter or particular properties of dark matter just by the fact that maybe we don't see any heating there. So the reason why the Earth is great is we have the data, it's very close by, and generally we understand what we're doing when we use something like the Earth. All right, so here are the implications for dark matter using heating in the Earth. I'm going to walk you through the meaning of this plot because I'm going to show you a few of them across the other objects. And I assume most of you are not familiar with seeing something like this. So in particle physics, when we want to try and make some statement about the nature of dark matter or the nature of any particles, we have a plot where we try and effectively map out the discovery space. And so I told you before, we don't know what the mass of dark matter is. So we can just really call it like a free variable. The dark matter mass can take on lots of different values. So that's what this x-axis here is on the bottom. So this is the dark matter mass in proton mass units. And on the y-axis is the dark matter, it says dark matter, should be dark matter, scattering rate. So if dark matter interacts very frequently, it would be higher up on this plot. If it doesn't interact very much, it would be further down. And what you see shaded in purple here is actually an exclusion coming from the fact that dark matter hasn't heated up the Earth. So when we look at the measurements down in these boreholes in the Earth, there isn't an anomaly, at least from dark matter, according to these parameters. So we actually can exclude that dark matter doesn't have these masses, reading off this x-axis, doesn't interact with this particular strength in here. The other regions on the plot aren't labeled. There are other different complementary experiments. I'm not going to tell you what those are, just in the interest of time. But the important takeaway of this plot is actually by using the Earth as a detector for dark matter, we can say something you couldn't have said using any other experiment about the nature of dark matter. So in this case, it's just dark matter doesn't interact like this, doesn't have this mass, just because we don't observe it. All right, In the interest of time, I'm going to maybe I'll spend 2 slides on neutron stars. So I told you that density actually really matters when you do these searches. Now, if you want to pick a star that's dense, you want a neutron star. So the neutron stars are really the most dense star that we have in the universe. So they're really small, so something like 10 kilometers across in radius, but they pack in the mass of the sun. So you think about the whole sun pushed into something that has a radius of 10 kilometers. That's a lot of particles. That's very dense. And the way that we actually get neutron stars, these just come from the collapsed cores of very heavy stars at the end of their life. So not something like our sun, it's much too light. But if you had something that was maybe 10 times heavier, 25 times heavier even than the sun, at the end of its life, you get a supernova explosion. So it's just, it goes bang, and then you end up with a core of just very dense particles effectively. And these still just stick around as a dense core. So because they're so dense, they have really high escape velocities. And this just means that it's very hard to get out of them if you get stuck in there. So if you're a dark matter particle whizzing around and you go on the inside, chances are you'll stay in there. So that means that these neutron stars are very good at pulling in lots of dark matter. In terms of neutron star searches, we don't have any data yet, but maybe we'll have it in the future. So this is kind of an idea for a future search to try and find dark matter. In the Earth's case, we already had a constraint. This one is some potential discovery for future. In terms of the limitations of thinking about neutron stars to find dark matter, they're very small. So if you're small, it just means it's hard to see. So if you want to try and detect any dark matter heating coming from neutron stars, they have to be pretty close by. You put them far away, you just won't see them. So you have to detect something close by, and we don't have any known candidates yet that are close by enough to actually use. Now, you also have to look at them for a long time to actually get enough data as well. The main benefit is you just have really excellent sensitivity to dark matter interactions. So this is a plot just like the one I showed you for the Earth. But in this case, what you'll see, and maybe you don't remember the axis, that's okay. The main point is that when you think about dark matter masses you can test with neutron stars versus the interaction size of dark matter with the regular matter as it comes into the star, the sort of sizes that you can access are much lower. So these dashed lines are different temperatures for the neutron star. So dark matter could heat it up to all these different temperatures. And if we actually observed a neutron star that was, say, very old and shouldn't be so hot, potentially that would correspond to a dark matter discovery with this sort of dark matter mass and dark matter interaction size. So really, it's just like a discovery space you can think about. All right, now for something else. You actually can think about this idea with exoplanets. Exoplanets are planets that are not in our solar system. So they're planets that are going around a star that is not our sun. And actually, they can be one of the best ways to look for dark matter. And this might be very surprising. Why would we want to use a planet around a different star? It actually turns out there's a bunch of benefits to thinking about exoplanets to find dark matter rather than the Earth or something like neutron stars. So the first advantage is really just the exploding research program at the moment in exoplanet science. So those of you who are big astronomy fans or like physics fans, perhaps you remember, if going back a few decades, we only actually learned about exoplanets very recently. And so we only discovered them very recently. So the first known exoplanet was found in 1992. So that's only like 31 years ago, very, very recent. And actually the bulk of the exoplanets that we've now discovered really were in the last few years. And this is rapidly increasing. We have many new telescopes that are going to come in line, find many more exoplanets. So it seems like there's a lot of systems here that we can think about as dark matter little discovery machines. And this gives us ample motivation to consider what are the new ways we could think about using all these planets as we discover them. The second advantage is just the sample size. So the number of exoplanets actually that are out there is just nuts. So the estimates predict that we should have around 300 billion exoplanets in our galaxy. So most stars on average do have another planet that go around them. So to date, of course, we haven't actually found all of these billions of exoplanets, and we probably won't find billions anytime soon. But we have found a lot of them so far. So I actually had a look today on the NASA exoplanet catalog. And to date, as of today, we have more than 5,000 confirmed planets outside of our solar system, which to me is really just wild and very exciting. So we have a whole lot of great candidates. And the reason why having this really large sample size is great for us is if you thought about something, just say like Jupiter, and maybe you heat it up just a little bit, and I tried to tell you, oh, I noticed Jupiter's a bit too hot. I think I found dark matter. You probably wouldn't believe me, and I think that would be fair, because you could say something like, oh, maybe we just don't understand what's happening in Jupiter. Maybe it has some strange formation history. Maybe something else happened off in the atmosphere that made it go just a little bit hot when you were looking at it. But if you had, several thousands of candidates, and I said all of the thousands of candidates are too hot, then you'd probably say, okay, that's probably a little bit suspicious. Maybe we should look at that a little bit more. So having a large sample size really helps us. They're also very cold, which means because they're cold, it's great. We don't want things that are too hot if we want to see any heat coming from dark matter. They're also great just because they're huge compared to some other targets we might want to use. So these neutron stars, I said they're very dense, but they're very small. So I tried to actually show them to scale on this slide. I couldn't really do it without really showing you the neutron star. So the neutron star would be maybe like 1 pixel here. And this would be the size of the sort of exoplanets in comparison that we want to look at. So they're something like 1,000 times larger in radius. So because they're so big, this means we can just detect them very easily. If we wanted to take something very big and we put it in the center of the galaxy where there's more dark matter, we've got a good chance of seeing it if we use an exoplanet. If we use something very small, like a neutron star, try and put it all the way across the galaxy, you're probably not going to see it. So exoplanets are actually better in that case. Okay, so exoplanets are very broad in what they are. So it's not just like they're all like a copy of the Earth. There's actually lots of different types of exoplanets. And just like you guessed it, what sort of target is optimal? Even within exoplanets, some are better than others to try and find dark matter. So something like Earth or super Earths. Super Earths are really just like Earth, a little bit larger, still rocky planets. This class of planets is not ideal just because they're not the biggest ones. Overall, we want something big or dense. And these are smaller, so they're not going to collect as much dark matter. The ideal classes that we want are something like Jupiters and super Jupiters. So Jupiters are really just like our Jupiter, kind of similar in size and density. Super Jupiters are just a little bit bigger, maybe 10 times bigger. So we would love to use these. They're some of the biggest types of exoplanets out there. They're great at collecting dark matter. We also want to use something called brown dwarfs. So brown dwarfs, if you haven't heard of them, they're kind of like what lurk between a planet and a star. So there's no nuclear fusion. They're not bright like the sun, but they do burn some things which make them not as cold, but they can still be quite cold. Overall, though, they're very dense, which means they're great at trapping dark matter particles. We also want to use something called rogue planets. So rogue planets, one of my favorite type of planets. So these ones don't have host stars. And actually what happens is they start going around some star, but they can just be ejected. So when they're ejected, they just wander through dark and empty space all alone. So they're very cold, so they're great for our searches. They don't have another star close by, radiating the surface and heating them up. Rogue planets also can just form molecular clouds like stars, but often they're just kicked out gravitationally. All right, so when we do this exoplanet search, are we just going to have the same thing I showed you before? No, you actually learn some different information by doing this exoplanet search. So I told you earlier in the talk that we don't know how the dark matter density in detail is actually distributed in our galaxy. So I said there's more in the center, and then there's less out where we are, but we don't know for sure what sort of shape it has. And we don't know for sure how much really is in the center. So we have some simulations to kind of predict different shapes. So this plot is showing you on the x-axis the distance to the center of the galaxy. So we're out here, this is just moving in towards the center. And you see that as you move towards the center, these are just 3 different totally arbitrary profiles from simulations. You see in general, it kind of goes up, at least as you move towards the center. So what you get from an exoplanet search, looking for dark matter, is potentially this will reveal to you what the density profile is. So this is mock data here. We don't have the real data yet for this search. But what we would expect to see is something where these black dots are all the exoplanets that get heated by dark matter, and they should just kick up as we go towards the center of the galaxy. So on the x-axis, we have the distance to the center of the galaxy. The Earth's position is here. So if you go to the left, this is going in towards the center. So go in towards the center, each dot's going up and up and up and up, because there should be more dark matter density there, more dark matter particles available. So this hopefully will actually give us a test of what the shape is of how much dark matter actually is towards the center, which could have quite interesting implications for the particle nature of dark matter. All right, we also have some sensitivity to the interactions, but I'm just going to go straight through very quickly in the last few minutes to a different type of signature that we can have using gamma rays. So I told you so far about this heating. So dark matter just heats things up. There's actually another scenario you can look for. When dark matter goes into a star or a planet, what can actually happen is, remember I said before, you have particle, antiparticle, smashed together, bang, lots of heat. What you actually can also have happen, when you think about it as a particle physics process, as two particles can come together and they actually can produce another particle that doesn't decay yet, but decays outside the surface of the star or the planet. Maybe this sounds contrived because I'm telling you there's some other mysterious particle in the middle that's going to allow whatever happens with the dark matter annihilation to happen outside the surface. But actually, when we think about these type of interactions in particle physics, we always have some type of particle in the middle. We call it a mediator. So it mediates the interactions between two different types of species. So this is a common sort of thing to think about in the regular matter as well. If none of that made any sense to you, don't worry. The general idea is just that what can happen when dark matter particles come together is sometimes the products of that annihilation can appear on the surface. And if they appear on the surface, this is something else we can actually see. It won't be heat, it actually will be really high energy light from the explosion. So this high energy light is something we call gamma rays. This is really, really high energy. We can't see it with our eyes, we can see it with our telescopes. Okay, so in terms of looking for the dark matter annihilation happening outside the surface of stars or planets, the sun is one of the best things you can use. So the sun is too hot to think about any heating, because we all know the sun's very hot. We feel the heat of the sun all the time. But it's very close by and it's very big. So it's great at pulling in dark matter particles because it's close by. It's pretty easy for us to try and detect what comes out of it. And we have excellent data available already using the sun. So the telescopes are called Fermi and Hawke. Their actual names don't matter too much. The point is just the sun's very close by and we can see very well what comes out of it. So this is one of these sort of discovery space plots again. And really what you see is that if you want to learn about the mass of the dark matter particle, the sun's really excellent because this is how much it interacts more if you go up on the axis, interacts less if you go down. And this dark matter lighter or heavier, the general space compared to any sort of existing experiment that we have that we can probe using the sun is really unrivaled. We don't have any other test for dark matter that's as sensitive as this one to these particular parameters. And this is just from the fact that we go looking at the sun, we don't see all of these big explosions of light, high energy light happening near the surface. So we say, okay, dark matter wasn't there. The last case that I want to tell you about is Jupiter. So Jupiter, in principle, you could try and heat it up, have the heating search. The thing is, because Jupiter is just in a local position, so it's not off somewhere in the center of the galaxy, it's fairly close by. It means it's in the part of, the dark matter sphere that isn't as dense. So you'll heat it up a bit if the heating happens, but not enough to be really sure that dark matter is what did it. But for Jupiter, something actually you could do is look for, instead of heat, the times when dark matter annihilates, smashes together, and produces something on the outside. The same case as the sun. And the reason actually you'd want to use Jupiter over anything else in the universe is compared to the sun, it's cold. So it's fairly big, but it doesn't really kick out dark matter particles very easily compared to the sun. So we all know looking at the sun, very hot, nuclear fusion going on. Jupiter's very cold in comparison. So when dark matter particles wander inside Jupiter, they generally can stay inside compared to the sun, where the sun can be just very good at just kicking out particles. Okay, so we thought this would be a very easy check to do. We thought surely sometime in the history of humanity, people went and looked at Jupiter in these high energy gamma rays, just high energy light. And we could just see in the data, is there anything there? Can we make some conclusion about dark matter? And actually turned out, before we thought about this idea, nobody had ever tried to look at Jupiter in this wavelength. So no one was looking at it in this high energy light before. So this seemed like a great opportunity because, I mean, while maybe dark matter is doing this, maybe we learned something else about our universe. This is a measurement that actually had never been done before. So we could find, high energy light could appear from things like acceleration of cosmic rays. So it's just high energy rays that are whizzing around in the universe in the magnetic fields. It could be interaction of cosmic rays with Jupiter's atmosphere, or maybe just dark matter. So actually, a lot of the telescope data with the Fermi telescope, this high energy gamma ray light, is publicly available. So what this means is if you're a theorist like me, you don't actually have to be part of the collaboration to try and use the data and do whatever search you might like yourself. So this is a great opportunity. So we downloaded the data, we had a look, we did the analysis. We tried to see, do we see anything coming from Jupiter and gamma rays? So here's what we got. This is the first look at Jupiter in this really high energy light. And just to describe what you're seeing, this is a really large region around Jupiter. And maybe we just have a look at the right map. So this is, if there was something really bright here, this would mean we were getting emission from Jupiter in this high energy light. And ideally, the best case scenario for us would be we see, some huge, really bright emission. We get a Nobel Prize because we found dark matter. We're not so lucky as you probably could guess. Instead, what you see here, you see all these little blue and red patches. This is just flares and other things that are happening as Jupiter's moving around. In the center here, Jupiter's pretty small. You would have seen something very bright if Jupiter was giving us this signal. So we had a look, we didn't find it. We, in fact, didn't see Jupiter at all in this high energy light, which was actually an interesting astrophysical conclusion for us. And then based on this, we said, all right, this is not how dark matter interacts. And we set some constraints on its nature, which is it cannot have these particular masses and these particular interaction size. So that's the shaded region, which was a shame, but you never know. You never know where you're going to find dark matter in the end. All right, so now as I'm moving towards the end of my talk, before I wrap up, I just wanted to really emphasize there are lots of interesting things that are happening in the dark matter space right now. And I really wish I had more time because there's too many things to try and explain and to share with you. But one thing is that I was speaking about these astrophysical searches for dark matter. We can think about looking for dark matter in the lab. We can think about these direct detection experiments, as Leane mentioned. And in fact, there were, for those of you who attended the previous lectures in this series, talks by Yele and Maria on how we can detect dark matter in the lab. So I really encourage you to have a look at the recordings. These are all online. If you're interested, so you can hear about more broadly how dark matter might interact. There's another type of signal as well, which isn't dark matter coming from stars or planets. So in terms of this dark matter annihilating, smashing together, making light, making something. Something that classically physicists have been doing for a very long time is just looking in halos. So remember from the beginning of the talk, I spoke about this really big cloud of dark matter that's around the galaxy. You can just look in that big cloud and see, do you see any light just coming from the cloud? Because there's already particles in there, so the particles could already smash together. And one mystery we actually have at the moment is that if you look in the center of the galaxy, where you would expect dark matter particles to find each other, because it's the densest part, we actually do see some high energy light at the moment. And maybe it's consistent with dark matter. We don't know if it is. We need to do a lot more careful checks before we actually conclude that it is dark matter. But it's a very interesting problem at the moment. Is dark matter already in the center of our galaxy annihilating? And overall, really, there are many different exciting ideas for dark matter that are going on at the moment. This is just really a tiny slice of the different types of things you can do with dark matter. Okay, so to summarize, today I've told you about different searches you can do using stars and planets. And really just overall, I think the important point is that we don't know what dark matter is. It could be so many different things, but given it makes up most of the matter of the universe, this is really one of the most pressing physics problems of our time. We'd love to figure out what it is. We need lots of new and exciting sorts of approaches to try and find it. So one at the moment is thinking about how stars and planets can be exploited as an example. So in this case, you can have heat detection being possible. You can have gamma rays, that's high energy light detection being possible. And based on some of these searches, I showed you today that using the Earth, we actually can rule out some properties dark matter doesn't have because the Earth's just not getting too hot from dark matter. And using the sun and Jupiter, think about these explosions that were happening outside the surface. They don't seem to be there when we look with our telescopes. So that excludes those particular properties for dark matter. And going forward in the future, exoplanets and neutron stars still could be used to find dark matter. The sort of discovery space is totally complementary to the other searches that we already have. So hopefully we will find dark matter there. I'm very hopeful and very excited to see what happens as we get more telescope data. And overall, really, we're going to have so many new technologies and new telescopes that I told you about that will launch in the next decade. So I'm really hopeful and very excited to see what we actually get here. Maybe we really will see dark matter showing up in one of these systems. Who knows where it's going to be? But overall, just I hope we find it. I think there are lots of exciting ways that we might be able to do that. So that's all I wanted to say. Thanks a lot for your attention.
Well, thank you very much, Rebecca, for a very eye-opening and also informative talk. And now we will have our Q&A. So anyone has any questions, we will take that.
I'm just wondering, for the gamma rays from the center of the galaxy, where does that dark matter on the chart? That's a great question.
Oh, would you mind repeating the question?
Of course. So the great question was that, so I mentioned to you before that there's dark matter annihilation in the center of our galaxy producing these high energy gamma rays or high energy light. Where would that appear on those sort of discovery charts I was showing you about before? So the answer to that question is it's difficult to compare them directly because what I was showing you on those plots was, I guess, scattering rate. And so the scattering rate was like dark matter bouncing off things. And if you're in the center of the galaxy, you don't have to bounce off the particles. It's just a process called annihilation. So it's a different type of process. So I would have to make another set of plots and then compare them in a different sort of way. So I couldn't directly compare them to the plots that I showed there, but it wouldn't be ruled out by those searches, for example. So thanks for the question.
Question over there.
You didn't say anything about black holes. Can black holes be used for detection? Because in some ways they seem to be ideal, because they are swallowing up huge amounts of dark matter, right?
Yeah, so there are different things you can do with black holes. You wouldn't want to do things like, for example, these heating or like these, the gamma ray signals where it's kind of appearing outside because you're just never getting out of a black hole. So if you want to try and get particles get outside, it's just not going to happen. People do think about new signatures with black holes. And in fact, actually, people think about black holes being dark matter as well. So there's a whole class called primordial black holes, which are black holes from the very early universe. And they themselves actually could be dark matter. We haven't actually ruled that out yet. So there are different ways that black holes can be used to think about dark matter signals, and including actually potentially being in themselves. But when you think about the types of signatures you have, they're very different to the type of ones that I showed you here.
And there's actually quite a related question from one online audience named Adonai, asking, how do we justify that dark matter is actually matter? Have we proven that it does take up space?
Great question. So when we think about, that's a good question. I think the right way to answer this. So if we think about what is there that we kind of know in the universe, the things that we know to exist, at least when we look at the regular matter, everything is particles or forces. So forces, they're just like some effect between particles. So there isn't really anything else that you can be. So you can be some sort of energy in the sense of thinking about dark energy. And this is something that's making the universe expand at an increasing rate. But in terms of actually being something like matter, the reason why we think it's some matter is when we think about all the different types of evidence we have for dark matter, you need a matter type component. And one way, this is hard to explain in, I guess, simple terms, but one thing you could think about is that as the universe expands, there's some component that has to behave a certain way. So in physics words, it scales a certain way, and you have to have it be a type of matter. So we think dark matter is a matter. It's not energy or radiation. Not sure if that answers the question.
Well, thank you. And I'm glad you actually mentioned dark energy, because there's another question from Chanel asking, if mass is equivalent to energy, how do you know that dark matter and dark energy are not closely related?
Great question. The reason why we don't think they're closely related is they behave almost in a totally opposite way. So dark energy is the sort of something that we don't understand perfectly that we think makes the universe expand. So that phenomena we're thinking about is, why does the universe expand faster? So everything's kind of pulling apart faster and faster. But if you put more matter in something, you have the opposite effect. You pull things in. So dark matter and dark energy really behave in two totally different ways. They're very different phenomena. That's a great question.
Thank you. Great, over here.
I guess from what you said, that dark matter interactions could either result in like heat reaction or gamma rays.
Yep.
So are those two different in terms of processes, because like energy was lost already in the heat reaction phase? Or do they correspond to different candidates for dark matter?
Great question. So they can be similar candidates, but on a particle physics sort of description, it's like a mathematical description, the scenarios are a bit different. So all that's different is that in the case you have the dark matter particles smashed together and you want to get the gamma rays to go outside, you have to have a mediating particle or mediating force that makes them go outside. And in the case where you just heat up the planet and the particles smash together, you can't have this long thing that's pushing them outside. So in sort of mathematical terms, the description of the theory is different in that case. So it maps onto a different class of dark matter candidates. That's an excellent question. Thank you.
Question over there.
Do you think that dark matter is the sort of problem that will be solved in years, decades, or centuries?
Can you please repeat?
The question is, do I think that dark matter is the sort of problem that will be solved in years, decades, or centuries? I wish I knew. I wish I could tell you. It's really hard to say. I mean, the other thing is the sort of roadmap to understanding what dark matter is, because we have discovered it in the sense that we see it out in space doing things. We just don't know what it is. So we've made a step already. But if we want to make future steps, you could imagine with some of these searches I showed you, for example, this exoplanet heating search, imagine that you did see all the exoplanets increasing their temperature as it went towards the center of the galaxy. You could say, okay, what does that tell you? You'd probably say that's a pretty good hint. It looks like it's dark matter, but that wouldn't be where the story ends. What we would start doing then is saying, okay, looks like it sits in this sort of discovery space of properties. Maybe we need to build a collider. Maybe we need to think of a new experiment that we do just, on top of the table here that shows us, is this consistent with other particle physics properties or other fundamental types of interactions? And really, it will be a series of steps before we finally understand what it is. So you could imagine if you have to make all these steps, even if we found, say, in 2 years, a new hint that's consistent with it, probably we're looking at least decades before we get thoroughly to the bottom of it. I hope it's sooner though, but hard to say. It's a good question.
And related to that, we actually have another online question from Gennaro asking that you have shown in many ways that, we could possibly detect dark matter signals from, heating and cooling processes. But do we actually have instruments that are so good that they can pick up these extremely minute changes in temperature or lack thereof?
Yeah, great question. So we definitely do, and we can see them. So in terms of these gamma ray signals, these actually would be very bright. So if the sort of sensitivity the telescopes have is way below how bright these signals would be from dark matter. And that's why in the case of the sun or Jupiter, we could say we exclude that dark matter doesn't have these properties because the telescope was sensitive enough to see it, but then it didn't. And in terms of the heating searches, so a number of these, like the exoplanets, is for going forward in the future, but we have done the estimates and it seems like you should be able to see this, for example, with like GWST or Robin. So they are sensitive enough.
That's wonderful. Also gives us hope.
Exactly.
Yeah. Any other questions from here? Okay, over there.
Yeah, I had a question about, as you showed this cartoon earlier in the slides about these galaxies moving into each other, and how the matter was interacting and there was still gravity. But it kind of seemed to me that the dark matter was just kind of passing through itself.
Exactly.
Do we know if dark matter interacts with itself or not?
Excellent question. So actually, the best information we have about if dark matter interacts with itself or not is from that system that I showed you. So that's a great thought to have. So really, from this, we know that dark matter shouldn't interact so much with itself. So exactly from your question, because what would happen, as you imagine, dark matter then would just get stuck and then it wouldn't be able to get past. So that actually tells us that dark matter doesn't interact too much with itself. It can interact a little bit because you can interact a bit and maybe mostly get through, but you can't have very strong sort of interactions or it would have been stuck as well. So that's actually how we know dark matter doesn't interact too much with itself, is from a system like that.
Great, we'll take one more in-person question. Okay, over there.
I would like to go back to like the origins of the universe,
Mhm.
when there was singularity. At that point, there was dark matter and regular matter.
Mhm.
How did they coexist in a single point and then reach the expansion of the universe? So I'm very interested in terms of the physical interactions between regular matter and dark matter.
Excellent question. So that far back in the universe, we don't know what's going on. So there's no interaction or anything like that that's happening. In fact, in terms of what really happens even after the moment of the Big Bang, we don't know for sure how dark matter interacts with the regular matter, just as we don't know right now how it interacts with the regular matter. So we don't really have any information as to what dark matter was up to in terms of its interactions all the way back that far.
Well, how about you also ask Rebecca after this event? Okay, great. And we will wrap up the Q&A with one last high-level question from an online audience member from Button asking, okay, well, you have shown me that dark matter is there, but how is the amount of dark matter in the universe calculated? What is the process? How do you know?
Oh, excellent question. So I showed you at the start of the talk, it's a very technical answer. I'll try and just give a very as simple as possible answer. The best information we have about this 5 times more than the regular matter comes from this cosmic microwave background. So at the beginning of the talk, I showed you that patchy looking sort of oval, and I didn't really explain what was going on because I just don't have time. But I told you that by kind of looking in the patchiness, we can tell how much matter is there versus, so dark matter versus regular matter. And actually that if you changed how much dark matter there was, so if there was 10 times more or 10 times less, all these patches would look very different. So I can't go into too much more detail, but if you're very interested in that, I would just say, look up the cosmic microwave background and dark matter, and you'll get a more extended response. Or you can ask me afterwards if anyone here is interested too.
Great, thank you very much, Rebecca. I know we have very limited time for the in-person Q&A, but Rebecca will be here after this event, so feel free to keep chatting with her. Well, but thank you very much for a very engaging Q&A. And just to quickly wrap up the event, so some of you were asking how often these public lectures are. Well, typically when we have a mini lecture series like this one on dark matter detection, it's typically once a month. But actually, we will be taking a break in August and come back with our regular programming in the fall. However, in the meantime, you could actually check out some of the other events that KIPAC is participating. For example, there is a semi-internal event at Slack called the Slack Family Day. It's open to Slack associates and also guests. So if you're employed there, or if you know someone who's working at Slack, ask them and you can actually join this mini science fair. And what will come back in September is we are actually doing a slightly different kinds of public event. It will actually feature multiple flash talks by KIPAC members and alum, talking about the big questions we have been working on, where we are, and where are we going next. So that one is going to be quite engaging and interactive as a panel discussion. And finally, in the mid-October, I hope all of you will have a chance to join us for the partial solar eclipse. In the Bay Area, there will be over 80% of solar eclipse. So still pretty exciting, even though we can't really see the annular. So finally, if you want to follow us for any upcoming events or simply just want to see what's up with us, you can follow all different kinds of social media channels and also sign up for the mailing list. So thank you very much for joining us tonight. Let's bring back everyone to the screen to say a goodbye. And we would also appreciate your feedback on our event, how it went, what you liked, what you didn't like, and also what other topics you would like to hear in the future public lectures. So we will be sending out a survey tomorrow, and we look forward to seeing all of you again. Thank you very much, and have a good night.